All right, so please notice the title of today's work. The font, in case you care, is bell-bottom laser. I don't know why the laser is involved, but it's bell-bottom because it's kind of hippy-dippy lettering. Like on old Beatles albums, if you know anything about the Beatles. You should know about the Beatles because they are, of course, one of the finest musical achievements ever. And they had that movie yesterday that was recently out that I have not seen, but I do want to. Yeah, there's a worldwide power outage, and then an Indian guy wakes up in the morning, and he's the only person that remembers the Beatles. Yes, and then I haven't seen the movie, but this is what I think. Being that he's actually talentless, he plays the songs that he remembers that nobody else remembers, so everybody thinks he's the Beatles, and since the Beatles wrote some of the most perfect songs ever made, he becomes a worldwide superstar, even though he has no talent of his own. Now, I haven't seen the movie. Could be the message is he actually does have talent, but can't break into the music industry, and now he can, or something, and then the message is like persevere and you'll get through it, or some crap like that. I don't know. But I haven't seen it, so I don't know. Have any of you seen Yesterday? It's really good. I have no doubt that it is really good. But again, it can't be bad because its soundtrack is the Beatles. I also saw Across the Universe. Do I seem like the kind of guy that would see that movie? No. Why did I see that movie? All Beatles music. Across the Universe. Never mind. All right, so as I was saying, bell-bottom laser. Please notice this word right here. Oh, I don't feel like red today. Ugh, barf. Real number system. Real meaning they actually exist. Now, you people think math is difficult, and we only use the real number system. There's a whole nother number system called the imaginary number system. Wait for that, if this bugs you. But don't worry, you don't have to worry about the emergent or the imaginary number system, not the emergency number system. The emergency number system is 911. In Canada, of course. In Britain, does anyone know what it is? No. No. No, it is what, RJ? It is 999. Anyways, imaginary numbers, real numbers, emergency numbers. Imaginary numbers you won't have to worry about till long way from now, and they play more of a role in physics until you get very high up in math. That's actually why they were invented, because of physics. So, let's get back to this. The real number consists of, as you can see there's a whole bunch of categories. There are 5 categories, as a matter of fact. Every number that we use in our math course is in one of these categories, okay? Now, they really don't hold a lot of use for us, except when we get a little further on in math, but since I don't like teaching this lesson, I like to get it out of the way early, okay? Okay. We will start with the first one, which are, now this is weird, this is technically the smallest group of numbers. But in a moment you're going to see how stupid it is to use the word smallest to describe this, okay? So, let's get on with that. If we were in kindergarten with Mrs. Bad Crumble, and we were sitting in our carpet on the circle, or maybe you didn't have a carpet, maybe you didn't sit in a circle at kindergarten, we did, and Mrs. Bad Crumble said, class, and you all went, yes, Mrs. Bad Crumble, because none of you had front teeth, so you all had lisps. Yes, Mrs. Bad Crumble. And she said, let's count together. And you would all say, yes, Mrs. Bad Crumble, except now, of course, you don't need to be able to count until the end of kindergarten. The latest learning outcomes for kindergarten expect you to be able to count to 10 by the end of kindergarten, after you've been in school for 10 months. So they figure you can get a number a month out of the average 5-year-old nowadays. And we wonder why math is difficult in grade 10, when the first 10 months of school, you managed to learn 10 numbers. But I don't make the rules. Anyways, so if we were all to start counting, when I clap my hands, you are all going to start counting. Yes, Mr. Bad Crumble. Ready? Stop. That's all I needed. What number did you all start with? 1, which is not the first number. 0 is the first number. But we all started with 1. A couple of wise asses might have gone 0, just so they could bully those of us that are doing it normally. I'm just kidding if you went 0. You're not normal, okay? It's just a joke. That's why my YouTube videos are classified as comedy. So, the natural numbers are simply, it is true, if you look, they're classified as comedy. It's hurtful, actually, because all I am trying to do is expand your people's minds. Natural numbers are what I like to call, and what every math teacher calls, the counting numbers. What do I mean by that? It goes 1, 2, 3, up to what? You stop counting at 9? How old are you? How old are you? So you don't stop counting at 9. So where does this number line end? Infinity. Does infinity exist?
Yes.
You could draw a number line and get to infinity.
Oh, hypothetically.
Ghosts hypothetically exist. Do they exist? No. Does infinity exist, or is it a concept? It is a concept. There is no spot in the universe that we define as infinity. Even if you read the book, The Restaurant at the End of the Universe, the restaurant is not at the physical end of the universe. Spoiler alert, it's at the end of the universe, when the universe ends, time-wise. That's why it's so cool.
What's the last number?
There is no last number, because the next number is that last number plus 1.
Is there names for like everything?
There are names up to a certain point, and then we just give up.
How long do you think?
Why bother? You couldn't ever count
so
there.
Weird.
That's what I'm about to say. Wait till we get to the next the next section here. And then you're going to be like, and I'm going to be like, yeah. And you're going to be like, and I'm going to be like, yeah. I think you are. All right. So, how many numbers are in this set? Infinite numbers, yes? And yet, even though there are infinite numbers in this set, I still told you it is the smallest set. How can the smallest set be infinite? And yet, it is. Caden? Huh? No. But you will see what I mean. It will show you how math transcends language. And we will do that in a moment. We will get to the next category, which is whole numbers. Now, when you hear whole numbers, what do you mean? Or what pops into your head? But not fractions. What part of fractions? Like 7 and 1/8. The 7 is what you all think of as the whole number, yes? Everyone agrees, right? Everyone. Yeah? And you're absolutely right, Vicky. That's what everybody says. But whole numbers are indeed that. But what they really are the counting numbers. The counting numbers. And what is the proper name of counting numbers?
Natural.
They're the naturals plus 0. So it is 0, 1, 2, 3, up to what? Infinity. Now, stop for a moment. How many numbers are in the whole numbers set? Infinite. How many numbers are in the natural numbers set? Infinite. So they have the same amount of numbers, don't they?
No.
You just told me they're both infinite.
But what about the plus 0 part? Are no numbers?
That's what I'm asking you. Do they have the same amount of numbers?
Yes.
How many numbers are in the natural numbers?
Infinite.
How many numbers are in the whole numbers?
Infinite.
So which is the bigger set? They're both the same, are they not? They both go up to infinity.
So whatever the whole number is, plus 1.
Now, we could argue that this is the difference, yes? But isn't 0 nothing? So I'll ask again, what's the bigger set? But the whole numbers have one more number. See what I'm saying? You don't really see what I'm saying. Do you see what I'm saying?
No.
What am I saying, Abby?
That the zero doesn't have value, so they're the same because they both go to infinity.
Okay, well, let's see what happens when we get down to integers. Now, you will notice I started with the smallest set, but it's not the smallest set because it's infinite, right? And then I added a number to it to get the next biggest, right? But it's still the same because they're both infinite. What's the third set? Integers. What do you think they are? Yes. Integers are the wholes plus negatives. So what does that mean? Where do they start if we were to draw it on the number line?
0. -2.
Yes, negative infinity up to what? Positive infinity. Now let me ask you this. How many numbers are integers? Infinite, right? But there's 2 infinities here, so there must be more integers than there are wholes and naturals, right?
Yeah, because you're going infinity this way and that way.
But infinity is infinity, isn't it?
But
The reason I bring this up, ladies and gentlemen, is simply this. Math, we talk about math in very concrete terms, yes? But really, when you think about it, math isn't concrete, is it? I keep saying math is always the same, and it really is. But the concepts behind it are kind of, I don't want to, overstate it. But when you start thinking about math, it's pretty crazy, right? Because of things like this. All 3 of these sets of numbers have the same amount of numbers in them. But they can't possibly have the same amount of numbers in them, right? Okay. Now, I'm going to draw a light blue, what, teachers now? Fudgicle. No, screw them. There's a million grade 12s down there. I'm going to keep working, and then I'll go down there. Because I'm the boss of me. Right, Gabriella? Damn right I am. All right. Now, you will notice 1, 2, 3, 0, 1, 2, 3, -1, 0, 1. What is missing from all of these? Decimals. But decimals are lame. What is actually missing? Fractions, because decimals are just fractions' ugly cousin. Okay? Everybody has one. I am the ugly cousin in our family because my cousins are stunningly gorgeous. Stunningly. I'm like, I don't even like going to family things because they're so pretty. Anyways. No fractions. Which, if there is no fractions, what does that automatically mean? There are none of decimals. Everybody cool? Jordy, hit me.
What's the point of dividing whole numbers, putting whole numbers as a section and natural numbers?
I don't know. I didn't make that choice. But the reason we have this is because sometimes in math we can't count fractions, right? How many kids are in this room?
Well, whole numbers.
Right? There's 30. There is no possibility that there is 30.2 kids in this room. The only numbers allowed to count kids in this room are whole numbers, right? You could argue integers, but you would never need all the negatives. So obviously you would be using whole numbers, right? That's why we have this, to classify numbers. Now, I've made that line because down here, rational numbers, what do you see? What word do you see in rational? Ratio, which means rational numbers are all of your fractions. And when I say all of your fractions, I mean all of your fractions, if they follow the following rule. X over y, and x and y are integers, okay, and y doesn't equal 0. That is all the fractions. Now, fractions have an ugly cousin. I'm going to use the ugliest color I have, poop brown. No, it isn't racist. And the fact that you would say the word racist even as a joke proves that you really don't understand anything about racism. But we'll move along because it's math class. Decimals are rational numbers sometimes. Does anybody know the 2 reasons where these guys fit? What makes a decimal a rational number? There are 2 conditions. Does anybody know what they are?
Well, you can put it over 1. Because, like, if you have decimal 2.1 over 1, then it's just 2.1.
But that's not 2.1 is an integer. I know you don't. You didn't bother coming to homework. I sent them to the office. Which, well, they told me to send them to the office. Perhaps you could come to homeroom and tell you to. No, that's not my problem. In the 12th grade, my mom didn't get me to school on time. All right. Decimals have to do one of 2 things. 1, they have to terminate. Now, that does not mean Arnold Schwarzenegger has all his skin melted off and walks down the hallway with his one red eye, talking in his Austrian accent about how he'll be back. That is not what I mean by terminate. What I mean by terminate is they end. 1.3751 is a rational number. Why? Because it ends. The other thing is if it repeats. 1.373737, and that carries onward. Everybody cool? Now, I'm going to go over here. You're going to talk amongst yourselves for a moment. I'm going to put a few examples up here. You're going to decide if they are rational numbers or not, and you're going to tell me why. Is that clear? Okay, here we go. 2 over 3. Rational or irrational? Rational. What happens if I turn it into a decimal? It's still rational. Why? Because 2 divided by 3 equals 0.66 forever. It repeats. Yeah? Okay. 1.37827594. Why? Because it ends. What is that as a fraction? 1 and 3782759 over what? No. 1 and 8 zeros. Because 1.1 is 1 and 1/10, yes? Okay, good. Now I'm going to mess you up a little bit. See who's been paying attention. 2.1 over 3.6. Those are integers?
No.
And yet you said it was rational.
Not rational.
Why do you think it's irrational? Well, of course it's rational. Why is it rational? What? It's a decimal that is rational because it ends over a decimal that is rational because it ends. And if I have a rational number divided by a rational number, it must be a rational number, yes? Another way you can look at this is it is 21 over 36, isn't it? Which is 7 over 12. Right? And that is obviously rational. Everybody cool? Sure you are. 2/5 over 3/4. Why? Mantoj.
Because first when you divide the top and the bottom, then those answers become another fraction.
Absolutely right. Isn't this really 2/5 divided by 3/4? And isn't that really 2/5 times 4/3? And isn't that really 8/15? And isn't that a rational number? So if that equals a rational number, and if that equals a rational number, they both equal rational numbers, so therefore they must both be rational numbers. Is everybody cool? Yes. Excellent. Now, the last bunch, the irrationals. For you people, well, first of all, irrational number is everything that isn't on this page already. All right? What's the most famous one? Pi. Because pi equals circumference divided by diameter, doesn't it? And that looks like a rational number, doesn't it? But when you do that division, you get 3.14159, blah. I don't care that you've memorized to the 100th digit. I don't care. It never, ever ends. There is a computer that has been dividing pi since the 60s. It's up to trillions of decimal places. It doesn't repeat. Right now, at this moment. All it does is keeps dividing pi. Everybody cool? That's the most famous one. For our purposes, irrational numbers are these. Square root of anything, any root of anything that isn't perfect. Here's what I mean by that. What is the square root of 4? 2. Rational. I shouldn't say isn't perfect. Any square root that isn't rational. So square root of 4 is 2. Is 2 a rational number? Yes. Square root of 2.25. You probably don't know that in your head, but if you do it with a calculator, you will find that it is no. 1.5. Rational. So this is rational. Everybody cool? Square root of 3. If you do that on your calculator, you get 1.73 blah, and your whole calculator screen fills up. This is irrational. Is everybody cool? Square root of 5, rational or irrational? Irrational. Square root of 9, rational. Everybody good? All right. Turn the page over. Whilst I am getting my picture taken, you try to do these. There are tricks that you can do beautifully. How could it not? I'm gorgeous. All right, what's this? 12 over 100. Of course, you would never leave it that way because Mrs. Bag Crumble would have marked that wrong, even though it's not wrong. What is it really? 3 over 25. What's B? But there's a line there. What does that line mean? 0.111111111111111 for how long? Forever. So it cannot be 1/10, can it? It can't be. Right? But, what is it?
Is it 1 over 9 because it's repeated?
It is 1 over 9. But everybody, why do you know that?
Because the number's repeated and
Nyeh. Okay. Did you have a teacher in your past tell you that? Right, and they didn't tell you why? No. Of course not. So, this is what we are going to talk about. You're intelligent young people, yes? Stop disagreeing with me. No, it is not debatable. You are intelligent young people. You are the best and brightest. So, what's that? 1/10. Agreed? Okay. Now, rational numbers have to have integers in the numerator and the denominator, yes? All right. 0.11111 forever. Is that greater or smaller than 0.1? Greater. Very slightly greater, yes? All right. So it's 1 because it's still a 1 there. Now, it has to be an integer under here, doesn't it? Well, what is the integer that will make this fraction greater than 10? It has to be an integer right attached to 10, doesn't it? So it has to be 9 or 11, yes? But since it has to be bigger, it must be 1/9, because that's the next integer on the line. Does everybody understand? That is why 9 becomes our repeater. Everybody cool? All right. Now, C is a little tricky. Because why? What makes C weird? What do you have? Oh, Mantage. The dot, dot, dot. What does the dot, dot, dot mean, Avner? That it goes on. Does it mean that it repeats? Not necessarily. So this question, can I definitively say that this is 2/9? No. That would be an estimate, wouldn't it? Because we do not know if the 373rd decimal place might be a 7. Everybody cool? So this is our estimate. Now, in reality, we're going to say that's 2/9, yeah? Right? Okay. Now, look at D, because D is the super tricky one. Because what repeats? Only the 4. So, is it 54 over 99? No. Because the 5 doesn't repeat. This gets me 0.545454 forever. That's not what I want. Has anybody been taught the trick for this? Well, let's try to build the trick for this then, right? Because there is a trick for it. We know we got to be over 9, yeah? Right? There's got to be a 9 in the denominator somewhere, yeah? Right? Yeah. Okay. When there was one repeating number, how many 9s were in the bottom? 1. Okay. So, there's two numbers now, but only one repeats. So logically, what should I put right there? A 0. That just makes sense, doesn't it? That one number repeats, the other one doesn't repeat. What number is nothing? 0. Okay. So we're doing a good job so far. That's a good guess, right? Now what are we going to do with top? Well, we know, could it be this? No, of course not. Because isn't that 6/10? And isn't that 0.6? Okay, so it can't be 54. All right. Okay. Well, what repeats? All right, so it makes sense that there might be a 4 up there, yeah? Okay. What doesn't repeat?
5.
The 5. Is your hand? No, it's not. So I got 0.54 or 54 up there, but we know it can't be 54, yeah? What doesn't repeat there?
5. Oh, the 0.
What math takes something out? No, what math takes something out? Subtraction. So, subtract 5. That gets me 49 over 90. Let's look. 49 divided by 90. Oh, there it is. Everybody cool?
So you subtract the number that doesn't repeat?
You subtract the number that doesn't repeat from everything else, from the whole thing. And that will always work. Everybody good? So what if I had 0.321 and the 1 is repeating? What would that be, do you think? Remember, math, always the same. You've just seen how to do it. How would you do it here? 90. 900. Why do you say 900, RJ? Because now I got 3 decimals. Okay. And then what would be up here? Look at the previous example. 321 minus 32. And it always works. Everybody cool? All right. Now, your job right now is to do number 2. And on page 29, really, I only need you to do 6. Actually, 6 and 15. These you should be able to do in your head. And you've got the answers right there anyway. But 6 and 15, the answers are over here. I am interested in the explanation. Right? Okay, do 6 and 15. It is 9:03. I am going to give you... What's the next thing we're doing? No. We're going to do these. Oh, you're going to do that page. But first we're going to do these. You got half an hour left in class. It's too much time for that page, but it's not quite enough time to do this page. So, what we're going to do is do the notes for this page. Then you're going to have work time. And then we'll do the work for this page tomorrow. Okay? Okay. Who remembers what a prime number is? This is another cool thing about math. Montage. What's a prime number? It only has 2 factors. So everybody knows that word factors, right? What is a factor? Any number involved in multiplication. Any number involved in multiplication. 2 times 7. What are the factors? 2 and 7. Right? 3 times 2 times 4. What are the factors? 3, 2, and 4. Everybody's good, right? Easy peasy, lemon squeezy. A prime number is any number only 2 factors. And those 2 factors are 1 and itself. What is the first prime number? 2. Why is 2 an incredibly unique prime number? Caden. It's the only even number. I would argue it makes 2 the most powerful prime number in a group of the most powerful numbers. Prime numbers are extremely powerful in a lot of things. Code breaking. They are extremely powerful in programming. They are just unbelievably powerful. We do not understand prime numbers at all. And here are some of the reasons. 1, if numbers go to infinity, and there's an infinite amount of numbers, then must there also not be an infinite amount of prime numbers? Yes or no? Yes. And prime numbers at the early end of the number line, are they fairly common or are they pretty rare?
What was the question, sorry?
At the early end of the number line, from 0 onwards, they're pretty darn common, aren't they? As a matter of fact, in the first 10, we get 2, 3, 5, 7. There's 4 numbers in the first 10. That's pretty common, right? What happens to it as we get bigger and bigger? Less and less and less. But it continues on.
Could the grade 11, M through Z, with their teachers, please come down for photos? That's grade 11, M through Z, with their teachers. Thank you.
The largest prime number, of which we know right now, has something like 14 digits in it, which is, to me, pretty darned cool. That you can have 14 digits long, a number that size. That is 3, 6, 9, 12. 3, 6, 9 is billions, 12 is trillions. That is up in the trillions. There is a number up in the trillions that you cannot divide by anything but 1 and itself. I think that's pretty neat. As a matter of fact, it is one of the very last math things for which mathematicians are seeking. They are trying to seek a way to predict prime numbers. And there is not a way to do that. All the math that we have done in all the civilizations, in all the universities, in all the think tanks in the world have yet to prove a certain man, his name was Riemann, R-I-E-M-A-N-N, he was a German mathematician. He has a hypothesis of predicting prime numbers, but no one has been able to prove it, ever. It's, I get a little up on prime numbers because I think they're neat. Yes. Oh, it's super complicated. Let me show you what it looks like in math, just for fun. Because what we're doing today is actually very easy. R-I-E-M-A-N-N. That's bad. But that is what it looks like. And these graphed curves show prime numbers. Because, of course, there are negative prime numbers as well. Prime numbers are neat. When the aliens come to talk to us, just like in the movie Contact, they're going to use prime numbers. Yo.
So then what's
1 is neither a prime nor a composite, because 1 only has one factor. 1. Everybody cool? All right, now, you all remember grade 5. Mrs. Bag Crumble made you make factor trees. Factor trees? Yeah, I know. But did you ever use them again? No. Did Mrs. Bag Crumble ever tell you why you were making factor trees? No, she just said, let's make factor trees. And you all being the good students you were, then yes, Mrs. Bag Crumble. And you made a bunch of factor trees, and she put gold stars on your paper, and you went home, your parents put it on the fridge, and you were like, I'm awesome. Right? I know this because I remember doing this when I was in grade 5, and I did it for my kids when they were in grade 5. Of course, the problem with math in Canada is we teach you something when you're 9, and then we don't talk about it again until you're 16. And then we're like, why don't you remember that, kid? Right? You have heard this. All your teachers have done this to you in math all the way along, haven't they? Okay. So, let's remind you how this is done. All you do to make a factor tree is you break each of these numbers down by division into factors. Now, we want prime factors, which means our factor tree is going to end when all the branches end at a prime number. Everybody cool? So, everybody do the first 2 branches. I'm not going to tell you what numbers to put there because I want to prove a point. What are your first two factors of 54? Don't say them out loud, just write them down. I am going to bet that the vast majority of you have chosen 9 and 6. But you could have done You could have done 3 and 18, but I bet nobody did. You could have done 2 and 27. Did somebody do 2 and 27? Sweet. So, I'm going to stick with 3 and 18 because nobody chose that one. Can this branch end? Why? Because it's prime. This branch has to continue. 3 and 6, prime, 3 and 2. Is everybody good? Yes. Great. Now do the same thing for 162. I'm going to change colors. I'm feeling mighty orange. Since 162 is bigger and also not on the 1 to 12 timetable, I am betting that 90% of you are going to go 2 and 81. Because that ends in 2, so you divide it by 2. Then, of course, 81, I bet 90% of you are going to go 9 and 9. 3 and 27? Interesting. I know. Neither of them can end. 3, 3, 3, 3. Everybody cool? All right. These have given us the prime factors. Now, the next thing you would need to do is you would want to write these as products of primes. So I'm going to highlight that because I'm going to use that word a lot over the next few days. What does it mean if you have a product in math class? The answer of a multiplication. Yes. Once you have all your factors listed, the answer is the product. So I need this number as a product of primes. And here I have primes, don't I? So 54 is, and I will write that in black because I use black, 54 is 2 times 3 times 3 times 3. But we're math people, right? We're the best and brightest math people. Would we ever write that?
No.
What would we write?
2 times 3 to the power of 3?
Yeah. Now, of course, you already know what to do. 162. What is it?
2 times 3 to the power of 4.
We're going to skip all this baby stuff because, I can't remember the show it was in, but my kids always make this joke whenever we play any card game with a wild card. Wild cards is for preschoolers. And I don't know what TV show it's from, but they've been doing the joke for 10 years. Do any of you know? It's from a kid movie or a kid TV show. They're playing cards and they're, yeah? What is it?
2 times 9 to the power of 2.
No, because 9's not a prime number. 2 times 3 to the 4th. Cool? Okay, everybody good? Everyone's good, yeah? Okay. Up to there, all of you should have done this at some point in your past. Yes? Okay. Now, highlight greatest common factor, which is never said. We always say it as GCF. Okay? You know what this is. What does the word greatest mean? Biggest. So is that to the right or the left on the number line? Right. To the right. Excellent. What does common mean? Oh, yeah, everybody's similar? Yes, there you go. Here, let me give you guys an example. You people are all very intelligent young people. I am a very intelligent old person. What is common? We're all very intelligent and we're all people. What is not common? That I'm old and you're young. Got it? So if you were to list everything about you guys in math class, very intelligent young people, everything about me in math class, very intelligent old person, what's the common stuff? Very intelligent people. Easy peasy, right? You guys have all seen Venn diagrams. You know what they look like, yeah? 2, 7, 8. Whoop. 3, 4, 8. What's the common? 8. Because it's common to both of them, yeah? All right. So we are going to do that in math class. A greatest common factor is the largest factor shared by a group of... Now, I don't want to say numbers here because we will use these with variables as well. Shared by a group of... I'm just going to say math, not mathematical. Shared by a group of math expressions. And you all understand what I mean, right? Like 2x is a math expression, right? But x isn't a number yet. Everyone's cool, yeah? Okay. So a GCF can be found using prime factorization 2 ways. One, we could actually use a Venn diagram. Right? So in black, there was 2 and 1, 2, 3, right? And in orange, there was 2 and 1, 2, 3. They're all shared, right? But out here, oh, I should use a different color. I tried to. Out here, what's left out all by itself? What's not in this Venn diagram? I see 1, 2, 1, 2, 3 black 3s, 1, 2, 3, 1 orange 2, 3 orange 3s, but what's missing? 1 orange 3. This guy is not part of it. Everybody cool? But Venn diagrams are great when there's only a couple of numbers, right? Everybody can draw a Venn diagram. But numbers get big. And there's a lot of factors involved. So there's another way to do it. And how we do that is we count all the common factors. And the shortcut is we look at the... Now let's look. We're counting all the common factors. 2 and 3 are common. What was the answer? 3 3s, right? I got 3 and I got 4. So I look at the exponents. Which one gives me the answer? The bigger exponent or the smaller exponent? The smaller one. Because factors are smaller than the numbers we are dealing with. Everybody cool? Look at the exponents and we choose the smallest. Now, a lowest common multiple is different. Factors go down. What are multiples?
The numbers that you can multiply with. Like,
If factors go downwards, what are multiples? They go up. So what is the first multiple of 2? 2, because 2 times 1. What is the second multiple of 2? 4, because of 2 times 2. What is the third multiple of 2? 2 times 3. Fourth? 8. Everybody cool? So we all know what multiples are, right? So the lowest common multiple is the smallest... Am I using the same blue? I am, sorry. The smallest product which shares a group of expressions as factors. Now, an LCM can also be found using a Venn diagram, right? So let's say I had 2 and 3. What are the multiples of 2 and 3? What's the first multiple of 2? 2. Next? 4. Next? What are the multiples of 3? 3 and 6. There's 2. There's 3. What's shared? 6. So we could use a Venn diagram, but again, useless with big numbers, yes?
Isn't that like necessarily that you can just cancel the prime numbers that are the same? So since there's 4 3s there, could you cancel out 3 of them?
Yes. How is it done using prime factorization? We count all factors. In this one, we counted common. In this one, we count all. We count all factors, but we cancel repeaters. What? What do you mean by that? Well, we'll show you. We're going to do GCF in red, and we're going to do LCM in blue. So in red, we had 2 times 3 cubed, right? That was 54. Agreed? And in our 162 was 2 times 3 to the 4th, yeah? So GCFs have to be the smaller ones, right? And we only count common. Is 2 common?
Yeah.
So I count 2. Is 3 common? So I count 3. How many 3s? I look at the smallest exponent because I got to look downwards, right? Because it's a factor. So what's the smallest exponent there? 3 cubed. And we know that's 54. Now let's check. Is 54 a factor of 54? Yeah, because 1 times 54. Is 54 a factor of 162? Yes, because 3 times 54 is 162. Everyone is good? Okay. Now let's do it with LCM. We list it the same way. And now we count all of them, but we cancel repeaters. So do I have to count this too?
No. Yes.
I got to count it once, but I got to cancel the repeater. So there's 2. Do I count 3?
Yeah, but only one.
Yep. But I got to cancel the repeaters. Does this 4 cover this 3? So it goes 3 to the 4th. So there's a shortcut there too. Factors, we're looking at the smallest exponent. LCMs, we're looking at the larger exponent, and that's 162. Is 162 a multiple of 162? Yes, because 1 times 162 is 162. Is it a multiple of 54? Yes, because 54 times 3. Is everybody good? All right. Now, your homework tonight is to answer those 2 questions on page 29 and attempt just page 31. Do what we just did on those 4 sets of numbers. Cool? What? Yeah, you can write right on page 29. That's why I try to leave enough room there. Everybody good? All right.